Diatomic molecules are a little more complicated, so we need to discuss them with more detail. So the first thing is to realize that they have a lot more degrees of freedom because they have different modes. And one mode is rotation, but there's three different axes, right? So if we think about our molecule oriented along the x-axis, it can actually spin end over end around the z-axis, end over end around the y-axis, so this is kind of like a circle oriented towards you versus a circle you see edge on, or it could rotate around the x-axis. So in this case, these are kind of spinning in place. So those are 3 degrees of freedom there. Then a fourth one is that, hey, there's a spring. It can vibrate. And remember that whenever you have a spring, you're going to have actually 2 degrees of freedom, one for the kinetic energy and one for the potential energy. But unlike the solid, we don't actually get 6 here because there's only one direction where there's actually this spring. So what does our total look like? We still have translational directions, right? This entire molecule is still zooming around in space. So we have 3 translational directions, x, y, and z, which is separate from everything else. That's like pretending it's a point particle on its own. But then we have these 3 rotational directions corresponding to different axes, and then we have 1 vibrational direction which actually has 2 different degrees of freedom in it. So our total here is actually 8, so 3, 3, and 2. So we have 8 degrees of freedom for a diatomic molecule if you just count. And this is an important point. I want you to understand what degrees of freedom are, both in terms of how we count and where they come from. And so this 8 number is important. If you just use some basic physics, everything we've been learning, you would say that there are 8 degrees of freedom for diatomic molecules. So then what? Now let's look at the molar specific heat. We've seen that for monatomic gases, the equipartition theorem worked pretty much perfectly. For the solids, it worked okay, not great, but we knew it was an overly simplified model. So now let's look at our molar specific heat for diatomic gases. Experimentally, it's 20.8 joules per mole Kelvin. And again, like the monatomic gases, this number is really, really consistent. And when we first saw this in a previous chapter, we couldn't explain why diatomic gases had a different molar specific heat than monatomic gases, but we saw that they did, and that diatomic gases had pretty consistent values. So experimentally, we can measure this. Now, if we say that there are 8 degrees of freedom, we then say that our molar specific heat would be 8 times 1/2 R, so that would give us 4R, which is 33.2 joules per mole Kelvin. Now, are these numbers the same? Absolutely not. These are not equal. Now, from a physics point of view, these aren't even close. There's like a 50% difference here. So in this case, we can look at this and say, our model has completely failed. There's a problem here. So what if we just look at the experimental value and say, how many degrees of freedom does that correspond to? Well, if there were 5 degrees of freedom and not 8, 5/2 R actually would give us the right value. So again, 8 degrees of freedom is what you get if you count based on all of the physics from what we think that these modes are. But now we see that experimentally it corresponds to 5. So we have to explain this, and this is important for a few different reasons. The fundamental explanation is, well, quantum mechanics. And the book notes that this is actually of historical significance in that at the time, physicists couldn't explain this difference, that physicists had started to understand thermodynamics, the equipartition theorem worked, but not for diatomic gases. A new understanding of physics involving quantum mechanics starts to explain why. So this is interesting in that this is one of the first times in this class that classical physics has not worked. So again, 8 degrees of freedom, what you get if you just count. 5 degrees of freedom is what the experiments tell us. So this figures from the book, and the idea is basically the modes themselves can have different minimum amounts of energy that they can store. So if you go below a certain temperature, some of the modes stop storing energy. The equipetition theorem does not tell you this because the equipetition theorem is classical in nature, and you have to have quantum to understand this. So if you, for instance, go below about 100 Kelvin, remember that this is Kelvin, so 100 Kelvin is pretty cold. At that point, you actually have a molar specific heat for a diatomic gas of 3/2 R. Why? Because at that point it can only translate. No longer do you have rotation, no longer do you have vibration. So at cold enough temperatures, a diatomic gas actually acts just like a monatomic gas. Well, we heat it up a little bit, and so we go above 100. Note that this temperature scale is logarithmic, so here we're at about 1,000 degrees Kelvin. Now we have some rotation, and our molar specific heat is now 5/2 R. So now note that experimentally, right, what sort of temperatures could they have done experiments at that point? It probably would have been between 200 Kelvin and maybe, say, 500 Kelvin, right? Nowadays, we can do experiments at much, much hotter, but if you think back to, again, say, 100 years ago or more, these temperatures, this is what you would have had. So that's squarely in this region. Now note that we've only added 2 degrees of freedom. We said that there were 3 rotational modes, but if you remember, 2 of them were the molecule rotating in a circle. Those are the 2 that you have here. The other one is where the atoms themselves are basically spinning in place, and quantum kind of says that you're not going to get that one, at least not shown here. So then above this temperature, you get your vibrational modes. So vibration doesn't actually kick in until you're at incredibly hot temperatures, and there's actually a region where your molar specific heat is changing. So note 7/2 is still not 8 degrees of freedom, it's 7. So that last rotational mode where it's spinning in place, you don't even see that here. So the takeaway message is that if you simply use classical mechanics to count the degrees of freedom, you get 8. That predicts this 33.2 joules per mole Kelvin molar specific heat, which experimentally does not match up. Experimentally, we see 5. Those 5 degrees of freedom are from your 3 translational directions, 2 of the rotational directions. This doesn't include when the atoms are effectively just rotating in place. So we have to go to incredibly hot temperatures before we actually see this vibrational mode. Quantum mechanics is the reason for this. And so what you have to do is if you're actually solving a problem, you want to use this 5/2 R. In general, our problems lay in this region. And if you start to go to slightly higher temperatures, we have a problem that the heat capacity changes. That's pretty difficult to deal with. So in our problems, unless you're dealing with something crazy hot, you should use a heat capacity of 5/2 R. However, realize that if you count the degrees of freedom, you get 8. So this is, again, really interesting because this was one of the first failure places of classical mechanics, and it's the first time we're encountering a place where we actually have to use quantum mechanics to explain something.